So good morning, everyone. I'm Yicheng Guo, a postdoc in Santa Cruz. I'm working with David and Sandy. So today I'm going to talk about the fraction of clumpy galaxies from Candle's good source field. It's a preliminary result, and my collaborators are mostly come from Candle's team. So clumps are an important observational feature of galaxies, and they are mostly seen in rest-frame UV and rest-frame optical images. And they are also seen in emission line maps, for example, H-alpha images. So this is a gallery of different kinds of clumpy galaxies in M. Green's paper. And you can see clumpy galaxies from redshift 0.5 all the way to 5. And the typical stellar mass of clumps are around 10 to 7 and 10 to 9 solar mass, and the size is around 1 kiloparsec or less. So clump regions are shown to be regions with rest-frame UV optical color, and the specific star formation rate of clumps is higher than that of their surrounding areas by a factor of several. So most of clumpy galaxies have surrounding underlying disks, and this is based on both the morphological analysis, that is Surtec index, or the kinematic analysis, for example, H-alpha velocity map. So clumps are also very important laboratory to test our knowledge on star formation, feedback, and galactic structure formation. So a widely held theory of the formation of clumps is that clumps are formed due to gravitational instability in gas-rich turbulent disk. So this is a very good example from Ganzo et al. 2011 to show the formation of clumps. So from the H-alpha velocity map, you can see underlying rotating disks. Red is moving away from us, and blue is towards us. And if you look at the velocity dispersion, it's very high, which means the disk is turbulent. And once you get the H-alpha surface, gas surface density from H-alpha map, you can calculate the Tum Q parameter. And for the site of clumps, the Tum Q parameter is less than 1, which means those sites are gravitational unstable. So this is a very strong evidence to support the formation of the clumps. Gravitational instability, also we call it a violent disk instability, VDI. However, the fate of clumps is not clear. So you may have two possible scenarios. First, clumps can go into the center of galaxies to form bulge, or they can quickly disrupted by feedback or tidal force. Both scenarios have some evidence. For example, in our paper 2012, we found a color gradient of clumps. So clumps in the center are red, and clumps in the outskirts are blue. If you turn this color gradient into an age gradient, and the clumps in the center are older, clumps in the outskirts are younger. So this is exactly the prediction of the inward migration scenario. But Woods et al. 2012 found different results. The clumpy pixels in their study shows very young age, almost less than 100 meg-year. That means the lifetime of their clumps are short, and the clumps must be quickly disrupted. And this is consistent with a quick disruption. So in order to understand the evolution and the fate of clumps, we have to have larger sample and consistent clump fund algorithm and better measurement on the clump properties. But before we go into the detail to study each individual clump, there's still one basic and key question remain unclear. So that is, what is the fraction of clump galaxies in a given stellar mass and redshift bin? So this fraction of clumpy galaxies, F clumpy, is the probability of galaxies undergoing the violent disk instability. So it is linked with the macrophysics of star formation and galaxy formation, for example, gas accretion rate and gas fraction or star formation efficiency. So in this work, we use a sample from Candle's good source field to study F clumpy. So our sample actually include galaxies around the redshift 0 to 3.5 and stellar mass greater than 9. and the specific star formation rate greater than 0.1 per gig year. All these properties are basically derived from SD fitting and multi-wavelength photometry. So how do we identify clumpy galaxies? We have two ways. First is through visual classification. For some of galaxies in our sample, each of them is inspected by 3 to 5 kinds of astronomers. And we have this 3 times 3 matrix. In one direction, you have blue patches, galaxies with no patches, little bit of patches, and this is V band, H band, lots of patches. In other direction, you have number of clumps, no clumps, a couple clumps, many clumps, and you have a combination of number of clumps and number of patches. And then we collapse this matrix into a single score for each galaxy. 0 means nothing, 0.25 means a couple of clumps or a couple of patches. And all the way go to 1 means many clumps and many patches. So this value is called clumpiness. And the disadvantage of a visual classification is it is only limited to very bright galaxies with H band magnitude brighter than 24. And we cannot tell the position of clumps from a visual classification. Therefore, we have the other way, that is find clumps from an automated clump finder. First, we smooth the original image of galaxies to get a smooth image, and then we subtract the smooth image from the original one to get contrast image. Then we masked out all the low signal to noise ratio pixels to get these filtered images. And the clumps are now standing out in this image. We detect the clumps by using the extractor, and here we find 6 clumps for this galaxy. If you think one of them is barred, you will have 5. Then now we compare the number of clumps from our clump finder with the visual clumpiness from visual inspection. So there's a very good correlation. Also, the scatter is large. And these galaxies, 5 clumps, the visual clumpiness is 0.62 is here. So our strategy to combine both methods is to use the visual classification as the primary criteria and the clump finder the secondary. If a galaxy has a reliable visual clumpiness greater than 0.2, we call it a clumpy. If the reliable clumpiness less than 0.2, it's non-clumpy. If the galaxy doesn't have a reliable visual clumpiness, we use our clump finder. And if the clump finder finds more than 1 clump, not including barge, we call it clumpy. Now let's look at our result. So this is F clumpy as a function of redshift and stellar mass. Here, the sample is divided into different stellar mass bins, and in this panel, they are divided into different redshift bins. So the basic results are first, the fraction runs from 20% to 60% for different stellar mass and redshift bin. And also, you can see the F clumpy versus redshift changes for different stellar mass bin. But regardless of redshift bin, the F clumpy always peaks around 10 to 10.5 solar mass. So now let's look at those results one by one and discuss them in detail. First, for low mass bins, F clumpy increase towards low redshift. That has the implication that violent distal instability occurs later in the low mass systems. We may have some observational effect here. Due to the cosmological dimming, we are able to detect more faint clumps in low redshift than in high redshift. But even we take that into account to say, okay, we only count clumps whose UV luminosity is more than 3% of the total luminosity of the galaxies, we still get this trend, although a little bit changed, but it will not be a flat trend. So we believe this trend is real. And in the intermediate mass bins, the trend changes mildly with redshift. And it is in these mass bins that the clump formation is most efficient, because it is always the bins with highest F clumpy at any redshift. And we will talk about this later. So in the most massive bins, the peak is around 1 to 1.5, and it declines towards low redshift and towards a high redshift. In low redshift, it could be due to disk it could be due to the disk is stabilized by bulge or star formation, or it could be due to the gas accretion rate is dropped at low redshift and the gas fraction is dropped too. So this is the medium and the range of gas fraction from Gies et al. So you can see the trend is consistent with the drop of F clumpy at low redshift. And in the high redshift, why the F clumpy is low? So it could be also due to the disk stabilized by bulge, or the disk quickly collapsed into nugget. So here are a few examples of non-clumpy galaxies in the high redshift. This one looks like a bulge-dominated disk, and this one looks like nugget. Now let's look at the F clumpy versus stellar mass, and as we said, it's always peak around 10 to 10.5. And if we have any observational effect, it will only change the amplitude of the trend, will not change the shape of the trend, because at a given redshift, the cosmological dimming or observational effect works similarly on both low mass and high mass galaxies. So what is the reason of the peak around this 10 to 10.5 mass beam? So the direct comparison is to compare this F clumpy with a stellar mass to the gas fraction from Linda's paper. And if you believe clumps must be formed in gas-rich systems, and the gas fraction should be responsible for the drop of F clumpy. And it is really a very good correlation for galaxies at high mass end around Z of 1. And if you go to higher and higher redshift, and because we don't have so many measurements on gas fraction at high and high redshift, so we cannot really say the agreement is good or not good. But anyway, the agreement is okay, I would say, for both Z of 2 and Z of 3. So gas fraction is responsible for the drop at high mass end. But how about for the low mass end? The F clumpy is typically lower than the average of gas fraction, or it's just drop quickly than gas fraction. So that means even those low mass galaxies are gas rich, they cannot efficiently form clumps. Something must work in to prevent them from forming clumps or quickly destroy the formed clumps. It could be a radiative feedback. Chris Moody will talk about the effect of radiative feedback this afternoon. So if you think that something work on the low mass end, prevent the clump formation, that should also work on the star formation efficiency. So we take the star formation efficiency, which is star formation rate, over the baryon accretion rate from Peter Bruce's paper, and then we try to feed this star formation efficiency as a function of stellar mass to our clumpy fraction. And it works very well for low redshift, for low mass beams, and at all redshift. So that means something shaped the star formation efficiency, also shaped the clumpy fraction at low mass end. But in the high mass end, we always have point above the star formation efficiency. That means something working on the star formation efficiency doesn't working on clumpy fraction. That could be AGN, because we don't have any evidence to show AGN is destroying clumps. Instead, we have some evidence to show AGN is associated with clumps, that clump may be a fuel source of AGN. Or it could be at high mass end. We are only talking about star-forming galaxies here, but the number density of coincident galaxies actually dominate the high mass end. And those galaxies are non-clumpy galaxies. It may be able to drop the clumpy fraction to the prediction of star formation efficiency. And this is a very preliminary result of observation comparison with the simulation. And the simulation is from Severino and Avisha and et al. Simulation, and Neil Mandelker identified clumps from the 3D gas snapshot, and he will talk about this process in detail this afternoon. And we only count clumps with clump mass greater than 1% of the disk mass. And you can find very good agreement between the observation and the simulation. For low redshift beam, intermediate redshift beam, maybe a little bit shift, and high redshift beam. And also, if you look at clumpy as function of redshift, the agreement is very good also. So this is a very preliminary result, and we are still working on to improve the result or to understand whether the clumps I find in UV are actually the clumps Neil found in the gas map. So we will keep you updated. So this is a summary of my talk. And we'll answer a question of what is fraction of clumpy galaxies at given stellar mass and redshift beam. And the result is the F clumpy runs from 20% to 60%. And F clumpy versus redshift changes for different stellar mass beam. But F clumpy versus stellar mass always peaks around 10 to 10.5 for all redshift beam. And we discussed some correlation and association with the of F clumpy with gas fraction and star formation efficiency. So that's all I want. Thank you.
Yicheng, I'm wondering whether on the low mass side, high redshift, the statement lots of clumpy could also be affected by two things. One, resolution. Even HST imagery doesn't have sufficient resolution to resolve structures. And B, suppose that the gas structures actually go up, which I would have thought is what you would have expected, then gravitational instability would tell you that the relative size of a single clump would increase. So if you then put this together, the clumps increase in size and this galaxy size goes down, would it make it not hard to see how clumpy it is?
So you are talking about this part?
Yeah, I guess.
Or the whole trend? Yeah, that could be because of the resolution of HST and also the size of clumps. So if you, yes, that's correct. If you look at the comparison with simulation here, we assume we have infinity resolution in the simulation, so we can detect the clumps regardless of size. So the trend is.
I just want to say, also in the simulations, below a certain mass, you should take the numbers with a grain of salt. I mean, you can't detect clumps down to infinitesimal mass being down the simulations.
Okay. But yeah, that's still, I mean, the case is even worse for observed galaxies because the resolution is high.
Justin? So you made the statement with comparing gas fraction to clump fraction, and low mass radiating feedback or something which you destroy the clumps. But here, of course, you have very good agreement with the simulation. So is this exactly what's happening in the simulation?
So in the simulation, in this round of simulation, we don't have radiative feedback. That's true. So the yeah, that's things we can discuss.
We'll be back at 10 past 11, and if you are speaking next, come check out.